Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 11 on the sphere. All right, let's jump right into it. I love spheres. They're one of the nicest geometric shapes out there. Now, the last solid we will examine will be the sphere. Recall that a sphere is defined as all points equidistant from a fixed point in three-dimensional space. Now, if you remember, right, a circle is all points that are equidistant from a fixed point in two-dimensional shape. So spheres and circles obviously are really related to each other. The sphere one could think of as being simply the three-dimensional version of the circle. Now, the volume contained within a sphere is dependent only on that fixed distance, right, the radius of the sphere, and is a formula that needs calculus to truly appreciate. There's no way that we can come up with this formula without calculus. In this lesson, we are only going to use the formula. So let's take a look at the formula for finding the volume of a sphere. A sphere with a radius of r has a volume given by v equals 4/3 times pi r cubed. All right, well look, there's no getting around it. This is a messy formula for two reasons, right? It involves the number pi, which is irrational, and it also involves a fraction, which isn't particularly nice either, the fraction 4/3. Again, it would be great if it was like 1/2. I'd even take the 1/3 that we get with pyramids and cones at this point, but no, we get 4/3. This is where it's going to be very important for you to take your time on the calculator to understand calculator techniques, and we'll talk about those a little bit as we go through this particular lesson. But let's jump into it right now and take a look at exercise number 1. Find the volume of a sphere whose radius is 6 inches in A, terms of pi, and B, rounded to the nearest cubic inch. Now, as a former engineer, I wish that you could always be finding these things rounded to a particular degree of accuracy, because in the real world, that's what you would want. You wouldn't want to leave it in terms of pi. But let's take a look at how you can do that and how you can use your calculator to help you out. First things first, let's just plug in the numbers, okay? So the volume, right, as we see in that formula, is 4/3 times pi times r cubed. In this case, right, our r is 6, okay? So without evaluating anything, right, our volume is 4/3 times pi times 6 to the third. Now with the volume formula for a sphere, and I've seen kids work with this for decades, literally, there's two very common mistakes. I think I've even made these before. One being that they'll leave the pi out. Again, it's understandable. It seems like it almost doesn't matter, but trust me, it does, right? And the other thing that they'll do, which is also very common, is because they're so used to the formula pi r squared, right, the area formula for a circle, they'll accidentally square this here instead of cubing it. Now, I want my answer in terms of pi, which means I kind of want a pi in the final answer. And what that really means is that I really want to multiply 4/3 times 6 cubed on my calculator and then just kind of tack the pi on at the end. So let's grab our calculator really quick and just take a look at that. I'm going to take my fraction button, right, and I'm going to put in 4/3, okay, and then I'm going to multiply it by 6 raised to the third power, okay? And I'm going to hit enter. I'm going to get 288. Now again, keep in mind that this is a three-way product, 4/3 times pi times r cubed, and with multiplication, because it's both associative and commutative, it is completely okay to do the 4/3 times the 6 cubed first, and then just tack the pi on at the end. So our exact answer, right, or our volume in terms of pi, is 288 pi. Okay? Now, in letter B, we want this to the nearest cubic inch, and I could certainly type in 288 pi and get the answer. No problem, right? But I'd actually like to go back and type it in this way, because if the problem just said, come up with the volume to the nearest cubic inch, and they never said, put it in terms of pi, I wouldn't even consider coming up with this halfway measure. I would just plug this all in at once. And literally, in this case, what I would have, right, is I would have that fraction, 4/3 times pi times 6 raised to the third. I'd hit enter, and my volume this time is 905 cubic inches. All right. unfortunately, for the most part, right, the reason that we even have to look at a scenario like this is that you could easily have a multiple choice question on a test, right, where, here's the radius, what's the volume of the sphere, and they leave their answer in terms of pi. And I certainly have a couple of those on the homework just to give you practice on it. In all practical applications, this, though, is what you're going to be doing. All right, let's keep going. Now, circular cross-sections. Recall that all cross-sections of spheres are circular. The largest of these is known as a great circle and is caused by the intersection of a plane that passes through the sphere's center. And the equator on the Earth is a great example of a great circle. So are any lines, right, of longitude. Those are those lines that go through the North Pole, the South Pole, and sort of wrap around the Earth. Those are also great circles, but the equator is a really good example of it. But at the end of the day, right, if I took a sphere and I cut it any which way with a plane, that cross-section would always be circular, but we'll always get the largest circle when that cross-section passes through the circle's center. Now let's take a look at exercise number 2. This one's a fun one. A sphere has a great circle whose circumference is 95 centimeters. Which of the following is closest to the volume of the sphere in cubic centimeters? All right, now this one's cool, right? You know that the volume of the sphere depends on only one thing, and that's the radius of the sphere, right? But the radius of the sphere will be the same as the radius of this great circle, and I know what the circumference of the great circle is, so I should be able to figure out the radius. What I'd like you to do is pause the video now and see if you can figure out which of these answers is closest to the volume of this particular sphere. All right, well again, I'm going to write this thing down right away because it's ultimately the formula that we must use to come up with our final answer. But the real question, right, is what is that radius, right? That's our question. We don't know it. Now, what I do know is the following. I know that the circumference of a circle is 2 pi times the radius, and I know that is equal to 95 centimeters, right? In which case, I can easily solve for the radius of this circle by dividing both sides by 2 pi. Now this is going to be an obnoxious number, but let's figure out what it is. And I think I'm even going to use my fraction bar to avoid kind of any errors that might come up in terms of order of operations, right? So 95 divided by 2 pi gives me a radius, and I don't want to round this early, or I don't want to round it too early. I'm going to go 1197. All right, so yeah, there we go. 15.1197 is the radius of that great circle, which is also the radius of my sphere. Now, once I have that, I just have to take this messy number, plug it into this formula, and figure out my answer. Let me extend my page a little bit. My volume now is going to be 4/3 times pi times 15.1197 cubed. Again, make sure you're always cubing and not squaring. So let's get that thing in. I've got 4/3. Again, can't forget the pi. Times 15.1197 raised to the 3rd power. And I get my volume equals 14,478.32 cubic centimeters. And now I just sit back, I look at all my choices, the one that's closest to it I hope is obvious, and that's choice 4. All right, so it's kind of cool. What that means is that if you know the circumference, right, of a great circle on any sphere, you can actually calculate the volume of that sphere by first figuring out what the radius of the sphere must be, and then using it to calculate the sphere's volume. All right, let's keep doing more problems with spheres. Okay, now we can use the volume formula of a sphere in combination with a variety of other volume formulas to solve problems like the ones that we've seen in the last 2 lessons. So let's take a look at a classic in exercise number 3. The largest sphere possible is placed in a cube that has side lengths that measure 8 centimeters each. What percent of the cube's volume does the sphere occupy? Round to the nearest percent. All right, it's a percent problem. I know everybody kind of gets a little bit worried about those, but we'll kind of get to the percent when we need to. The first thing that we really probably need to do is figure out the volume of the cube, figure out the volume of the sphere so that we can compare the two. Pause the video now and see if you can figure out both of those. Now, the volume of the sphere is obviously going to be kind of ugly, so you're going to have to probably round it at some point in time, all right? So round to whatever you think is appropriate, and then we'll get into the percent issue after that. Pause the video now. All right, well, let's take a look at the easy one first, right? The volume of the cube is simple because that's just going to be literally 8 centimeters cubed. There's a reason that we call raising a number to the third power cubing it, because it finds the volume of a cube with that side length. Yeah, so I'm going to do 8 to the third, and I'm going to get the volume of the cube is 512 cubic centimeters. Excellent. All right, that's nice, clean, and easy. Now, the sphere, right? We know that the volume of the sphere is 4/3 times pi r cubed. So let me write that formula down. I always love to write the formula down first. That way I can be sure that I'm substituting into it correctly. And the key here is that the radius of this sphere is going to be 4 centimeters because it is the largest sphere that can fit into this box, right? And think about it this way, right? The diameter of the sphere, right, would go from one side of the box to the other side of the box, so the diameter would be 8 centimeters, the radius would be 4 centimeters. Again, we need to be very careful when we substitute this thing in, but let's figure out what that volume is. Here we go, 4/3. Again, let's not forget the pi. I'm saying this more for myself than for you, because it would be easy for me to forget. There's my 4/3 pi r cubed. Hit enter, and the volume of the sphere is equal to 268, and I think we'll just do 0.08 cubic centimeters. Now, percent, okay? Don't make this harder than it has to be. If you just took a test and let's say the test was out of 45 points, and you got 39 out of 45, you would do 39 divided by 45. And you'd get some messy decimal, right? And then you'd be able to think about what that decimal means in terms of a percent. And that's exactly the same situation here, right? I could think of it as being a test that has 512 points on it, right? The sphere got 268.08 points on this test, if you will. So I just want to divide this volume by that volume. Let's see what we get, okay? So let's take 268.08 and divide it by 512. And let's see what that decimal looks like. All right, in fact, I'm just going to take that answer, which is sitting right there, and hit divided by 512, and that's going to be 0.5235, etc. Okay, and what did we want it to? We wanted it accurate to the nearest percent. Now, right, think about this, right? The fraction that it occupies is 0.52, 52 out of 100. Now, if you need to, you could always multiply this by 100, but this is roughly 52 out of 100, which is 52%, right? Now, again, it's actually 52.35 out of 100, but rounded to the nearest percent. It's 52%. You can always take part divided by whole and multiply by 100 if that's helpful for you. That certainly will give you the percent, right? But I'm hopeful that you can take part divided by whole, look at that decimal, and interpret that as 52.35%, which to the nearest percent is 52%. All right, always good to do a little bit of percent work here and there. Let's now do some really applied problems. Exercise number 4. A grain silo that stores corn can pack at a density of 16 pounds per cubic foot. The silo is shaped like a cylinder along with a hemisphere of the same radius on top of the cylinder as shown. Letter A. Determine the volume of the silo to the nearest cubic foot. All right, well, This one's going to get a little bit messy, but again, I think it's probably pretty straightforward. I want to find the volume of the cylinder. I want to find the volume of the sphere, or sorry, of the hemisphere, the half sphere, right? I want to add those two together, and that will give me the volume of the silo, and then I need to round it to the nearest cubic foot. Pause the video now and see if you can figure out the volume of this corn silo. All right, well, let's do it. First things first, let's take a look at the volume of the cylinder, right? The volume of the cylinder is pi r squared times h, which is going to be pi times 5 squared times 15. All right, now I could totally figure out what that is, but keep in mind, that's going to be a messy, messy number, right? So I'm just going to leave it right like that, nothing more. Now, the volume of the hemisphere, or maybe I'll even just put the half sphere, all right? Right, we know that the volume of the sphere is 4/3 pi r cubed, and we're going to have to throw in a factor of 1/2 there. Of course we are, right? Because it's half of the sphere. So I'm going to now have 1/2 times 4/3 times pi, and it's also got a radius of 5. So 5 cubed, right? Now, if I want my total volume, I can just add those together, right? So let me take my calculator out. Whoops. Take my calculator out. I'll punch all of this in, and then maybe we'll go to the full screen so that you can see it. Let me just clear the screen up. All right, I've got my pi times 5 squared times 15. There's my volume of my cylinder, pi r squared times h, plus now 1/2, every time with the 1/2, 1/2 times 4/3 times pi times 5 to the third. All right, let me just go again to the full size so you can see that. All right, and again, think about how nice this is, right? When we've got these beautiful graphing calculators that have the ability to deal with fractions and all sorts of stuff, here I've got pi r squared times h, that's my cylinder, plus 1/2 times 4/3 pi r cubed, right? We've got it all there. We just hit enter. No need for us to figure out either one of the individual volumes separately. I now have 1439.8 da 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 da. All right, we'll get that down and then we'll round it. But how nice is that, right? So easy to just put it in all at once. You know, you don't have to then worry about any kind of rounding until the end. 1439.896, etc. We want it rounded to the nearest cubic foot, so the total volume is 1,440 cubic feet. Okay. Great. So let's take a look at letter B. How many tons of corn can the silo hold if there are 2,000 pounds per ton? Round to the nearest tenth of a ton. So many times in agriculture, especially when you're talking about grain like corn or wheat or soybeans or things like that, people talk about quantities in tons, right? And a ton is a big quantity, right? It's 2,000 pounds, okay? I want to figure out how many tons of corn I can fit in here. Now, I know that the volume is 1,440 cubic feet. I also know that there are 16 pounds of corn per cubic foot, right? So that's going to help me figure out how many pounds of corn I can fit in here. And then I'm told that there are 2,000 pounds per ton. So what I'd like you to do is play around with this and see if you can figure out how many tons of corn to the nearest tenth I can fit in this grain silo. Well, let's figure out first the number of pounds, right? So I'm going to say weight, right, is going to be 1,440 cubic feet times 16 pounds per cubic foot. Let's get that out. That's going to be even a bigger number. So 1,440 times 16 for a total of 23,040 pounds, right? And now, right, we can say the number of tons we have is going to be 23,040 pounds divided by 2,000 pounds per ton, unless, of course, you're using the metric system, but we're not, divided by 2,000, of course, 23, just never ceases to amaze me how I forget that every time. Have to hit approximately, and that is 11.52 tons, which to the nearest tenth of a ton is 11.5 tons. Wouldn't surprise me if somebody claimed that this was a 12-ton grain silo, right? But in fact, it holds 11.5 tons. All right, let's do one more problem. Everyone's going to like this one. It's about ice cream. Let's take a look at exercise number 5. Nico got the jumbo ice cream cone at the Dutchess County Fair, best county fair in the country. The amount of ice cream can be modeled using a cone whose height is 12 centimeters and whose radius is 4 centimeters. A hemisphere and then a full sphere of ice cream of the same radius were loaded on top of the cone as shown. If there are 237 cubic centimeters in a cup and 320 calories per cup of ice cream, how many calories is this treat if the cookie cone itself has 85 calories? Now, one thing I don't think that I made explicitly clear in this problem, and this was my own fault, so let me just clarify. We certainly have ice cream filling the entire cone, all right? So there's definitely ice cream down here, as well as the hemisphere, and as well as the sphere, all right? So this is a pretty lengthy and involved problem, okay? What I'd like you to do right now is pause the video and see if you can figure out how many calories are in this tasty treat. All right, well, we got a lot of things to work out here. The volume of the cone, the volume of the hemisphere, the volume of the sphere, the total volume, the calories that come from the ice cream. Actually, then we got to figure out how many cups of ice cream that volume represents. Then how many calories we got in the ice cream, add it to the measly calories that the cone represents. I think I'll just take the cone itself, right, at 85 calories, and then we'll finally have the total amount. All right, let's start working through it. So first things first, how about we work through that cone, right? The volume of a cone is 1/3 times pi r squared times h. So for our cone, we're going to have 1/3 times pi times 4 squared times 12. All right, that's going to be the volume of my cone. Awesome, right? Let's deal with the volume of my hemisphere. That's going to be a little bit ugly. That's going to be 1/2 times 4/3 times pi r cubed. So that's going to be 1/2 times 4/3 times pi, everything's got to have a pi in it here, times 4 to the third. And then finally, so this is my cone, this is my hemisphere, and then my sphere, that's maybe going to be one of the easier ones. That's 4/3 pi r cubed, and that's going to be 4/3 pi times 4 to the third. All right. So all of these represent the 3 different volumes that are in this problem. And of course, my volume total is going to be the volume of my cone plus the volume of my hemisphere plus the volume of my sphere. And yet again, what I'd like to do, instead of working out each one of these individually and writing down all of their messy decimals, I'm just going to try to be very, very careful and enter it all into my calculator at once. And again, I'm going to do that now here. And then we'll go to the big screen just so that you can see it. All right, here we go. First, the cone. So I've got my 1/3, all right, times pi, times 4 squared, times 12. I take a look at that calculation, 1/3, pi r squared times h, it looks good. Plus, now my hemisphere. That one's the most irritating one to me because it's got 2 fractions involved. The 1/2 that comes from the fact that it's a hemisphere, and the 4/3 that comes from the fact that it's half of a sphere, right? So 4/3 times pi r to the third, right? Maybe I'll even put that multiplication symbol in there, even though I don't think I need it. Okay, So now I've got 1/2 times 4/3 pi r cubed, plus now, finally the volume of my sphere, that's going to be, whoops, one more time, that's going to be 4/3 times pi times 4 to the third. Again, I look at it all good, all well. Let me escape here and have you look at this on the bigger screen. All right, whoops, and of course, how'd that happen? Awesome. That pretty much negated what I was just trying to do there. Let me just stretch this out a little bit, see if we can make it a bit bigger. All right, I like that. Let's take a look at this really quick. Okay, and then we'll hit enter and get the actual answer, okay? 1/3 pi r squared h, right? Here's our cone, plus 1/2 times 4/3 times pi times r cubed. There's our hemisphere, plus 4/3 times pi times r cubed. There's our sphere. We've got them all. We've checked them over. Each one of them's got the pi. Each one of them's got the right radius to either squared or to the third. Hit enter, and we finally get our volume of ice cream in cubic centimeters. So we have 603.2, let's say. That 0.2 is probably a little bit serious, but darn it, I want that 0.2. So let me go back to my handhold only. All right, let's go back into our full screen view and get that total volume. Oh my goodness, everything's going wrong right now. Let's delete that, let's try it again. Move this over here. That is 603.2 cubic centimeters. All right, well, that's getting us closer, right? But we want to know how many calories this treat has. We know that there are 237 cubic centimeters in a cup, right? So the next thing we need to do is figure out how many cups of ice cream we have, right? So the number of cups is going to be our 603.2 cubic centimeters divided by that conversion, right? Which is 237 cubic centimeters per cup. Right? We all kind of have a sense, hopefully, for what a cup is in terms of size. So when we see that there are 2.545 cups of ice cream, so roughly 2.5 cups of ice cream, that kind of makes some sense. Don't get me wrong, that's a lot of ice cream, right? That's quite a bit of ice cream. But now that we have the number of cups of ice cream, right, we can now take our 320 calories per cup of ice cream and figure out how many calories are just in the ice cream. And then we can't forget, you know, that 85 calories that comes from the cone. So let's get our total calories now, right? So our total calories are going to be that 2.545 cups times, what was it again? 320 calories per cup. And then we've got to add on that measly 85 calories for the cone itself, which is probably the best part, right? So I'm going to take that, I'm just going to take my answer and multiply it by 320 and then add on 85. Woo, man, and that is 899.428, etc. So 899 calories. Thank goodness it's not 900 calories. You know, I'd feel really bad about it if it were. Or at least I'd feel bad for Nico if it was that many calories, right? But no, we didn't quite get to the 900 calorie mark. 899 calories. All right, let's wrap this up. All kidding aside, right? We see spheres all over the place in the real world, right? Whether it's scoops of ice cream, which I get it, aren't perfect spheres, so maybe we were over 900 calories, or maybe we're a little bit less, who knows, right? But we see spheres all over the place, you know, whether we're looking up into the sky and we're seeing the sun or the moon, right? Those are roughly spherical. Certainly our Earth is spherical. There are all sorts of things from basketballs to baseballs to pickleballs. Yes, that's right, I said pickleball, right? That are spherical, right? And oftentimes the space that is enclosed within that sphere is an important measurement. Now, it's, obviously its formula is a little bit messy, 4/3 times pi times its radius to the third, but at least, we don't have to bring in more than just that radius, right? Again, an annoying fraction plus pi, but we can still get away with them. And we're going to be using this formula in our last 2 lessons of the course as we continue to model other things in geometry. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.